In many applications, the rate of change of a variable y will be proportional to the value of y. If y is a function of time, t, then the proportion would be written like this. dy over dt equals some constant of proportionality k times the value of the variable y. What we'd like to do now is find the general solution of this differential equation. I'll start by separating the variables, bringing the y variables on the left, and we'll put the t variable on the right. K is just a constant. Our next step here will be to integrate both sides of the equation. Now for antiderivatives, we'll get ln y and kt plus c. Now we'll let both sides of the equation be the exponent of an e. This will cancel the ln. I'm going to put a 1 on this constant to set it apart from other constants. And our final general solution will be y equals ce to the kt. Now that we've found the general solution, we'd like to find the particular solution that conforms to this curvature here. So we have 1.0, 2 with a t of 0, we have a y of 2. So I'm actually going to plug that in because we need to determine what the values of c and k are. This will reveal that c is 2. I'll plug in my c of 2 to get y equals 2e to the kt. Now I have to plug in another point on the graph, a t of 2 and a y of 4. And we should be able to solve the equation for k now. First I'll divide to get 2 equals e to the 2k. And then we'll want to take the natural log of both sides. This will have the effect of canceling the e. So we'll get ln 2 equals 2k. Therefore, ln 2 over 2 is k. At this time, we can write the particular solution. It's y of t equals 2e to the ln 2 over 2 times t. Y equals 2e to the ln 2 over 2 t. Alright, lastly we're asked to find the value of y when t is 3, so we want to make a prediction. And the final answer is actually given here. So let's see how we would find that prediction. We'll plug in a t of 3. Here as well. I'll do this on calculator. It's approximately 5.657.